Hello dear students, in this class I would like to solve some more problems on the topic oscillations. Displacement between maximum potential energy position and maximum kinetic energy position for a particle executing simple harmonic motion. Already I have discussed this concept in case of synopsis. The displacement between maximum potential energy. Suppose if you consider the simple pendulum experiment. This is the simple pendulum. At this point, the kinetic energy is maximum. Potential energy is equal to 0. Here, the potential energy is equal to mgh and kinetic energy is equal to 0. Displacement between maximum potential energy position and maximum kinetic energy position here from this point to this point. Now consider O to A. The displacement between maximum potential energy position to maximum kinetic energy position for a particle executing simple harmonic motion. The kinetic energy is maximum at both end positions. Here, the displacement between maximum potential energy position and maximum kinetic energy position for a particle executing simple harmonic motion. The amplitude is y is equal to a. Here the displacement is equal to amplitude. It is plus or minus a for both the ends. This is the one end A and this is another end B. Here y is equal to a. Displacement of the simple harmonic motion y is equal to a. It is plus or minus a because it moves in this direction. It is the positive amplitude. It moves in this direction. It is negative amplitude. The option C is the right answer. The next problem is the time period of a mass suspended from a spring T. The time period of a mass suspended from a spring T. If the spring is cut into 4 equal parts, the spring is cut into 4 equal parts and the mass is suspended from one of the parts, then the new time period will be. We know the formula. Time period of the spring, that is T is equal to 2 pi root of m divided by k. Here it cut into 4 equal parts. Here k is the spring constant. It cut into 4 equal parts, then k dash is equal to 4 into k. Then the new time period will be, that is t dash is equal to 2 root of m divided by 4 into k. Then finally we get the answer. The new time period t dash is equal to t by 2. Option D is the right answer. Next problem is, in case of forced vibration, all of you are familiar with the forced vibration, damped oscillations, undamped oscillations. Here, in case of forced vibration, the resonance wave becomes very sharp. Resonance wave becomes very sharp. Here, resonance wave becomes very sharp if the damping force is low. And the damping force is very low, then only the resonance waves becomes very sharp. Here, that's why the option B is the right answer. The potential energy of a simple harmonic oscillator. The potential energy of a simple harmonic oscillator when the particle is halfway to its end point. The particle is halfway to its end points. We know the potential energy of the simple harmonic motion, that is U is equal to 1 by 2 m omega square into x square. The total energy of that simple harmonic oscillator is, that is E is equal to 1 by 2 m omega square into a square. But here in this problem, the potential energy of a simple harmonic oscillator when the particle is halfway to its end point. Halfway means here x is equal to a divided by 2. X is equal to a divided by 2. Therefore, u is equal to 1 by 2 m omega square into a square divided by 4. 1 divided by 2 m omega square into a square divided by 4, or here it is 1 by 2 m omega square into a square. This equation is equal to energy of the simple harmonic oscillator. Now I can write this equation. U is equal to E divided by 4, or U is equal to 1 divided by 4 into E. U is equal to 1 divided by 4 into E. Option D is the right answer. Here E is the total energy, the potential energy of a simple harmonic oscillator, and the particle is halfway to its end point. The option is 1 by 4 types of its total energy. Option D is the right answer. Next problem. A particle of mass m oscillates with simple harmonic motion between points x1 and x2. The equilibrium position being at 0, its potential energy is plotted. It will be as given below in the graph. When a particle of mass m oscillates with a simple harmonic motion, here in this case, with a simple harmonic motion between the points x1 and x2, the equilibrium position being is 0. Equilibrium position being is 0. When the simple harmonic motion, object is set into the simple harmonic motion, potential energy is 0 at the mean position and increases on both sides becomes maximum at both the extreme ends. Here in the diagram 1, it is in the negative axis. This is wrong. Here in case of C, this is also wrong, and D is also wrong. The option B is the right answer, because the potential energy is 0 at this point. The potential energy is 0 at the mean position and increases on both the sides. At this point, the potential energy is equal to mgh. Here also the potential energy is equal to mgh. Potential energy is 0 at the mean position and increases on both sides becomes maximum at both the ends of these 2 points. The option B is the right answer. Next problem. A mass of 0.5 kg. A mass of 0.5 kg moving with the speed of 1.5 meter per second. It is velocity on a horizontal smooth surface collides with a nearly weightless spring of force constant, that is K, 50 Newton per meter. The maximum compression of the spring will be. Here a mass here, suppose if I consider this is the body, it has the mass m is equal to 0.5 kg moving with the speed of, that is v is equal to 1.5 meter per second on a horizontal smooth surface collides with a nearly weightless spring of force constant. Here K is equal to 50 Newton per meter. It is a force constant. The maximum compression of the spring would be, we know the formula here. When the body moving on the surface, it has a kinetic energy, that is half mv square. It is equal to the maximum compression of the spring. The potential energy of the spring is, that is 1 by 2 k into x square. K is the spring constant, x is the displacement of the spring. Now I am going to find the x value, the maximum compression of the spring would be. Here substitute the values in this equation. Here 1 by 2, that is 0.5 into m is, that is also 0.5 into v square. V is 1.5 whole square, it is equal to 1 divided by 2, that is 0.5 into k value is 50 into x square. 50 into x square, then x square is equal to, that is 0.5 into 0.5 into 1.5 whole square, we get the answer 0.25 into 2.25 divided by 25. Finally, when you are calculate this problem, finally we get the answer x is equal to 0.15 meter. X equal to 0.15 meter. Option C is the right answer. Next, which one of the following statements, which one of the following statement is true for the speed v and acceleration a, speed v and acceleration a of a particle executing simple harmonic motion? Particle executing simple harmonic motion. In case of simple harmonic motion, the displacement is, here in case of simple harmonic motion, the acceleration is directly proportional to its displacement and always directed towards its mean position. Always directed towards its mean position. But when the velocity of the body is maximum, acceleration becomes zero. Which one of the following statement is true for the speed v? For the speed v, velocity of the body is max, the acceleration of a particle executing simple harmonic motion. Velocity v is 0, a is 0. No, this is wrong. The velocity v is maximum, a is 0. Yes, here at this point, the acceleration is 0. Here also the acceleration is 0. Then when v is maximum, when the velocity of the body is maximum, acceleration becomes 0. This is right. Option C, when v is maximum, a is maximum. No, wrong. The value of a is 0. Whatever may be velocity of v. No. Option C is the right answer. Two springs of spring constants K1 and K2. Two springs of spring constants K1 and K2 are joined in a series. The effective spring constant of the combination is given by, we know the formula, and the two springs are springs of spring constants K1 and K2 are joined in series. Already I have discussed this concept in case of synopsis. Two spring constant, this is the K1 and K2 are joined in series. The effective spring constant of the combination is, that is 1 by K is equal to 1 by K1 plus 1 divided by K2 in case of series. In case of series, the effective spring constant of the combination. Now I can write this equation is also 1 by K is equal to K1 plus K2 divided by K1 into K2. The effective spring constant K is equal to, it is 1 divided by K. Now I can write this equation K1 into K2 divided by K1 plus K2. K is equal to K1 plus K2 divided by K1 into K2 divided by K1 plus K2. Option B is the right answer. Next problem, a particle executing simple harmonic motion. A particle executing simple harmonic motion of amplitude 5 centimeter. Amplitude 5 centimeter has maximum speed of 31.4 centimeter per second. It is a velocity. The frequency of its oscillation is. The maximum velocity in case of simple harmonic motion, we know the formula. V maximum is equal to A omega. Here A is equal to 5 centimeter and V maximum is equal to, V maximum speed is 31.4 centimeter per second. Then the frequency, that is omega. Omega is equal to V maximum. Omega is equal to V maximum divided by A. Now substitute the values here. That is 31.4 divided by 5 per second. But we know the formula, exact the frequency, that is omega is equal to 2 pi into f. Then the frequency f is equal to omega divided by 2 pi. F equal to omega divided by 2 pi. Here omega is equal to, we get the value 31.4. 31.4 divided by pi into, here the value is 5. 5 into, here 2 pi. 2 into 3.14. 3.14. Then f is equal to, this is 31.4. 5 into 2, 10. 10 into 3.14, that is also 31.4. 31.4 divided by 31.4, we get the answer f is equal to 1. Option D is the right answer. 1 Hz. The frequency of its oscillation is 1 Hz. Next problem is two simple harmonic motions of angular frequency 100 radian per second and 1000 radian per second have the same displacement amplitude. The ratio of their maximum acceleration is. Two simple harmonic motions of angular frequency 100 and 1000 radian per second. 100 and 1000 radian per second have the same displacement amplitude. The ratio of their maximum acceleration is. We know the formula. The maximum acceleration, A maximum. Here A maximum is equal to omega square into A. The ratio of their maximum acceleration means A maximum for the first simple harmonic motion and A maximum for the second simple harmonic motion, that is omega 1 square divided by omega 2 square, because the amplitude is same for both the cases. Therefore omega 1 square, that is 100 divided by 1000. 100 square divided by 1000 square. Here we get the answer 1 divided by 10 square. 1 divided by 10 square. Option C is the right answer. Next problem is a simple pendulum performs simple harmonic motion. Simple pendulum performs simple harmonic motion about x is equal to 0. It is mean position. With an amplitude A and time period t, the speed of the pendulum at a simple pendulum performs simple harmonic motion about x equal to 0. It is the mean position. With an amplitude A and time period t, the speed of the pendulum at x equal to a by 2, half of its amplitude. X is equal to a by 2. We know the formula. The velocity of the simple harmonic motion or speed of the simple harmonic motion, that is v is equal to omega into root of a square minus x square. Omega is equal to, that is 2 pi divided by t. 2 pi divided by 2 is equal to root of a square minus x square. Amplitude is a square. Half of its position is, that is a square divided by 4. We get the answer 5a into root of 3 divided by t. V is equal to 5a into root of 3 divided by t. Option A is the right answer. Next problem is, which one of the following equations of motion represents simple harmonic motion? Which one of the following equations of motion represents simple harmonic motion? Here the acceleration is directly proportional to displacement and always directed towards its mean position. The restoring force is directly proportional to its displacement also. Here, which one of the following equations of motion represents simple harmonic motion? According to the definition of simple harmonic motion, the acceleration is directly proportional to displacement and always directed towards its mean position. And according to the force constant or restoring simple harmonic motion formula, the force is directly proportional to its, or restoring force is directly proportional to its displacement. The negative sign indicates the force and displacement both are in opposite direction. Therefore, A is equal to K into X. Here the negative sign indicates opposite direction. The option A is the right answer. In this case, K, K0, K1 and A are all positive. That's why the option A is the right answer. Acceleration is equal to K into X. Next problem. The displacement of a particle along the x-axis. The displacement of the particle along the x-axis given by x is equal to a sine square omega into t. X is the displacement of the particle along the x-axis. A is the amplitude, the motion of the particle corresponding to. We know the formula here. X is equal to a sine omega square into t. Here the motion of the particle is corresponding to, and the displacement of the particle along the x-axis only, then its amplitude becomes its half of its initial value, that is a divided by 2, and sine square theta is equal to formula 1 minus cos square omega into t. That's why simple harmonic motion of the frequency is omega divided by 5. In case of this value, the option A is the right answer. Next problem. When two displacements represented by y1 is equal to a sine omega 1t. This is the displacement of the first simple harmonic motion, and y2 is equal to b cos omega into t, or superpose the motion. We know the formula, the resultant equation y is equal to y1 plus y2. When two displacements represented by y1 is equal to a sine omega t and y2 is equal to b cos omega t. Here y is equal to y1 plus y2. y1 is equal to equation a sine omega into t, and y2 is equal to b cos omega into t. Here we put capital A is equal to a cos 5 and B is equal to a sin 5. This is equation number 1 and this is equation number 2. Therefore, this equation becomes y is equal to y1 is equal to a sin omega t. Here a sin omega t into cos 5 plus y2 is equal to, that is a cos omega t into sin 5. Here take the common value outside, we get y is equal to a into, the amplitude is same for both the values, we get sin omega t into cos 5 plus cos omega t into sin 5. Therefore, y is equal to a into, it is in the form of sin a cos b plus cos a sin b. Therefore, a into sin a plus b. Sin a plus b is equal to sin a cos b plus cos a sin b. Here the compressed form of this equation is y is equal to a sin omega t plus 5. Here it is represents the simple harmonic motion. But by adding and squaring equation number 1 and 2, by adding equation and squaring equation number 1 and 2, we get a square plus b square. A square plus b square is equal to a square cos square 5 plus a square sine square phi. Therefore a is equal to a square plus b square. A is equal to a square plus b square. It is equal to a equal to root of a square plus b square. A is equal to root of a square plus b square. Now come to the question. Here, when two displacements represented by y1 is equal to a sin omega t and y2 is equal to b cos omega t, when these two equations are superposed with each other, we get the simple harmonic motion with the amplitude a is equal to root of a square plus b square. Option C is the right answer. Next problem is, when a particle is executing simple harmonic motion, its maximum acceleration is alpha and maximum velocity is beta, then its time period of variation will be. We know the formula. The maximum acceleration, that is a maximum is equal to, or the maximum acceleration is alpha. Alpha is equal to a into omega square. That is equation number 1. And maximum velocity, phi maximum velocity, instead of phi maximum velocity symbol we use the beta. Instead of a maximum symbol we use the alpha. Maximum velocity beta is equal to a into omega. This is equation number 2. Dividing equation 1 by 2. When we dividing equation 1 by 2, we get alpha divided by beta. Alpha divided by beta, it is equal to omega. Alpha divided by beta is equal to omega. Therefore alpha divided by beta is equal to omega is equal to, it is 2 pi divided by t, and the time period t is equal to 25 into beta divided by alpha. T is equal to 25 into beta divided by alpha. Option